If you look at questions from a perspective of which strategy is it, it makes the questions quite doable. If you don't sort of get it into what strategy to use, they can be quite hard to solve. Okay, we've already seen the first one. If you have an I and an E value, we saw that with hydrogen iodide a couple slides ago, you can just solve the whole ice table. That would get you all your E values, so you could solve for that equilibrium constant. Okay. So I'm not going to write out what I did before, but it was do a column, then do the C's, and then finish all your columns. So the 1, 2, 3 that I put on the previous slide. Okay. A second strategy that you'll have to use sometimes that you've not seen yet is if you know the I values and an equilibrium constant, you're going to have to use a variable in your ice table. So you're going to use an X for your C's, for your changes. And if your change had a coefficient of 3, you'd say 3x for your change. If the coefficient was 2, you'd say 2x. Or if a change of 1 unit, 1x. Okay, so you're going to have to use a bit of your math algebra skills here. Last of the 3 most common strategies, 95% of your questions are going to be one of these 3 strategies. So you know all the E's but one. You know the E's but one, okay, and you know the Kc value. Okay. Okay. You're going to be able to plug in and solve an equilibrium law expression right away. You actually don't even really need an ice table. You just need to know an equation. You're going to have an equilibrium law expression with one missing piece, whatever that missing E is. You're just going to rearrange it and solve for it. We're going to put an X in for our C's. Okay, and you should be pretty confused. You're really not sure what that looks like, but I'm going to do an example and you're going to see it on my. The question is, determine the equilibrium concentration of all species. So determine the E's and the equilibrium constant, Kc. We got 2 parts to do. Okay. And we're given an initial concentration of hydrogen, iodine, and we have a final value for hydrogen. And I'm using that reaction that we used for the case study that we're familiar with, and we know some things about this reaction. In my ice table, I'm going to put in moles per liter, because that's what I need for the square brackets for my equilibrium law expression. I would never put moles into your ice table. If you were given moles and a volume, I would convert it to concentration right away and get that in. If you do your ice table, so if you do your equilibrium law expression with just moles, it's not correct. So I'm going to pull all my given data. Initial concentration of hydrogen and iodine gas is 5.00. The final hydrogen gas concentration is 1.10. I've stated my units. It's been moles per liter all the way along. Last, so this is typical what you'll see. This product was never mentioned, so you would assume that there's 0 at the end. You've got to make that assumption. Now you've got to sit back and figure out what strategy you want to use. Okay. Well, we don't know all the E's plus 1, so that bottom one is out. Okay. It ends up being the first one. We know 2 values in a column. So this is the same strategy you saw me use before, and it's the first one on the list. Okay. 1, 2 values, so I can find the third. Then I can do all the C's, and then I can do the columns, which will let me answer the E's, the first question. I'll do that first, and then we'll solve for the equilibrium constant. 5 has to go down to 1, down almost 4, but not quite 4. 5 minus the difference between 5 and 1.1 is 3.90. So that completes my column. Now I've got to do all my C's. This is where I do the stoichiometry. One hydrogen gas needs to use up one iodine gas. They react in equal proportions. So this is going to be down 3.90 also. Stoichiometric coefficients are the same. Their change will be the same. Okay. This is double the hydrogen. So this will have double the change, but it's going up. So that's going to be 7.80 moles per liter made. So we end up with 7.80 and 1.10. Okay. So I'm not going to, I should, if I was doing an answer, write a sentence or a statement stating the answer. I'm going to leave that out, but please do that when you're doing a test or quiz. Okay. I know the equilibrium concentration of all my species. What is the Kc value? I need a law expression, and then I will do a calculation. So concentration of products, that's my product. There's two of them, so I square it. Reactants, H2, one of them, so to 1 power. I2 gas, no exponent, it's an implied 1. Now I'm ready to plug in. 7.80. I just really want to emphasize you have to use moles per liter here, so I'm writing them in, and then I have to square that. I move to the bottom, 1.10 moles per liter for my hydrogen. The iodine happens to be the same value, so I can sort of skip a step mathematically and just square it. Okay. Now, it happens to work out that my units cancel. Okay. We've got 2 moles on the top, 2 moles per liter, and it's squared. And we've got moles per liter squared on the bottom. So the units cancel each other out. Even if they don't, Kc values are always unitless. Okay. That's what the governing bodies say. So even if they don't cancel, do not put any units here. They are dropped. Okay. And that's just a rule we follow. Okay. Square the top times the bottom, and you get 50.3 unitless. Okay. None of the Ka values in your booklet, there's no units there. They're unitless numbers. They're just a constant. Okay. And I've answered this question. I just want to end with, what on earth does 50 mean? Like, is that big or small? Like, what's the range? So we're just going to end with a bit of a number line and talk about the range, and we'll put 50.3 on our number line. We're going to start with, on our number line, I'm going to put Kc on the bottom and percent yield on the top. Okay. The smallest percent we could have is 0, and the biggest percent we could have would be 100. Okay. So no products at all products. Okay. Now I need you to do some mental math. What Kc value would you get? So look up here, what would happen if you had no products and all reactants? What would you get mathematically? Scroll back. So what value would this have if there's no product? It'd be 0. If there's no product, 0% reaction, there's no product, our numerator will be 0. Okay? Products go on the numerator. Okay? So the Kc value for 0% yield is going to be a Kc of 0 because our numerator will be 0. We're not dropping it and replacing it with a 1. It is in the equilibrium law expression. Its mathematical value is 0. Okay? So hopefully that will help you. This is a bit harder mathematically. You're going to tell me one answer and I'm going to convert it. Your answer is going to be right, but I'm going to express it differently. What would you get if you have all products and no reactants? And I can think of 3 ways you can answer this, but I'm biased towards one of the correct 3 ways. So I'll just leave people to think. So just pause. What would you get if you had all products and no reactants? Undefined is one of the 3 ways that you could express it. Okay? So if you put in your calculator, if you try to, you're going to have a 0 down here. If you put a 0 in there, your calculator is going to say undefined. Okay? But there's a few more. We're going to express it better than that. You don't quite answer the question of at 0, limits, you sort of answer, well, what happens as this gets closer and closer to 0? If this isn't quite at 0 yet, maybe there's 0.1 of the reactant left. Okay? What happens when you divide by a small number? What happens to the ratio? It gets big. Okay? It's positive infinity. As Kc gets bigger and bigger and bigger, this value gets smaller and smaller and smaller, the denominator, which makes the whole expression bigger and bigger and bigger. And eventually you can't define it. It's undefined. Okay? But we can dig a little bit deeper. It's not just undefined, it's infinitely big. And in your acid-base table, you kind of see that. You've got K values for all your weak acids. When you get to the strong ones that are all products, no reactants, the book just says very large. It's really infinitely big. Okay? So the upper limit, how big can Kc get? It can go to positive infinity. There's no numerical limit. It could be 1,000, 10,000, a billion, 100 billion. It's all products. So we have to have positive numbers between 0 and infinity. Okay. Last of your math questions, what if you're in the middle? You're at 50%. Okay. And the top and the bottom are equal to each other. What would you get if the numerator and the denominator are the same values? You're going to get 1. So, which kind of makes for a little bit of a messy number line. If I stick a value of 1 for Kc, and it's hard to do the, where is 1 on 0 to infinity? It's a bit arbitrary. A value of 1 is your 50% reaction. Okay? Now, technically, that is only for a double displacement type reaction, where 2 things turn into 2 things. Okay? It moves slightly above or below 1 if it's 3 things becoming 2. Okay? The math doesn't work out to be exactly 1. Okay? But if you're between 0 and 1 for most reactions, you are reactant favored. If you're above 1 all the way up to infinity, that's a lot of numbers, your product's favored. So 1 is that kind of flip point. Okay? Now in this question, we're at 50. Okay? So I'm kind of guesstimating, maybe there's our 50.3, and we're in the products favored section. Okay? And we see that in our reaction, we used up most of the reactants. Okay? We went halfway would be using up 2.5. We've used up more than 2.5. Okay? We've made more than half of the maximum amount of product. We're greater than 50% yield. We're above 1 with our K value. So things are aligning. They make sense. The percent yield, the K value makes sense with the data we're given. So the concentration of N2 and O2 is 3 moles per liter, and I'm explicitly stating this is at equilibrium. And that's all we were given for initial information. And the question is, what is the concentration of the product? It's not saying when. That's a product, so I'm going to assume it means at the end. So in solving any of these problems, build an ICE table, so recopy that equation and get out ICE. I'll hide the equation because it's repeated, and I'll leave the given information on the top. So I always write my units next to the ICE table. So we're going to use moles per liter. Okay. Those are the only units you can put into an equilibrium law expression. You can do an ICE table in moles, but you can't take those E values and plug them in to get a K value. So we have 3 moles per liter of N2. Also 3 moles per liter of O2. That's all that's given to us. So we have no idea right now what the N2 would be at the beginning. We don't know what the O2 is at the beginning. The product, we're not told anything, would assume that'd be 0. But that's not our question. I'll switch colors. Our question really is, what is the NO concentration at equilibrium? Strategy-wise, we don't know a column, so we can't just fill out the whole ICE table. We've seen examples of that already. We don't know an I and a KC. We don't have any I's that we know their value other than the 0 one, which doesn't help. Okay? But we know 2 of the E's but 1, and we know the K value. So this is the bottom strategy on the list I gave you. It's the least tested. Okay. No E's, should be all E's, but 1, and a KC. Okay. And you can just solve that by plugging right into the equilibrium law expression. If you recognize this from a question, you almost don't even need to do an ICE table, because we're going to go right into the expression. KC equals concentration of our product squared divided by our first reactant times our second reactant. There's no powers because they're each one of them. I'm going to plug everything in. KC is 6.2 times 10 to the minus 4 equals. I don't know what this is. This is a variable. This is what I'm trying to solve. So the most common variable, I said it, but I didn't put that square in at the top. This is what we want to find out. So to solve that, I'm going to replace NO with a variable with X. That's what I want to solve. So I just replace what we want to get with X. I still have the square. So we're going to solve for X squared. X will be ultimately our answer. Divide by 3.00. This is also 3.00, so I'm just going to square it. Okay. Normally, I'm a huge proponent of writing in units. I tend not to do it with equilibrium. At this point, I have you do a double check that the right units went in. Okay. We have to use moles per liter, and we did. Unit analysis might fail us because even if there were units in this value, they were dropped. So you can write the units in, that's fine, but don't freak out when they don't cancel because of this unitless value. Okay? I've dropped my units, but I made sure I use moles per liter. x squared equals cross multiply x squared is crossed with a 1 down below, and I do that cross, and I'm going to just do that multiplication, and I got 5.58 times 10 to the minus 3, square root both sides, x, which is my concentration of NO, is 0.075. Now I carried extra digits. My Kc value has 2 sig figs, so I'm reporting my final answer to 2 sig figs. This carried an extra digit. Okay, and this is where moles per liter are going to be our units, regardless of what unit analysis would tell us. So we've seen 2 of the 3 methods, an I and an E. You just solve. We've seen all the E's but 1. You could skip the ICE table and go right into this, but I'd suggest you lay it out and make a plan. So we have a carbon monoxide and water equilibrium of carbon dioxide and hydrogen gas. Okay. We are given data that there's a 500 ml container, 2 moles of each reactant, and we're given an equilibrium value of 4. Now it is worth noting, you don't necessarily have to write this down, but that 4 is greater than 1, so we have products favored. Morning. You too. So you should realize we should get an answer that makes more products than reactants, and it's a nice double check to do at the end of your question. Okay. You don't have to do that, but you may catch a mathematical error if you're not getting more products than reactants. Okay, and my question is to calculate the equilibrium concentrations, plural. First thing I want to do in this question to solve is get the right units right away. Okay, make sure I don't start plugging moles into my ICE table. My ICE table would be right, but wouldn't be in the right units for equilibrium. So I'm going to calculate my first reactant. So 2 moles is in half a liter. So that's 4 moles per liter. And my other reactant is the same 2 moles in half a liter. So the 2 reactants are still the same concentration. They start with the same amount of moles, and they're in the same volume. Occasionally, students might want to add the volume up, but you have to realize this is a gas reaction. They're sealed in the same vessel. That swirl at the top is a seal, and this container is 500 milliliters, and there's 2 moles put into both. So don't add the volumes together. It's the same container. I pre-typed in the initial concentrations. Now I use that ambiguous 500 that I try to avoid where you're not sure of sig figs. I'm going to treat this as 3 sig figs, even though those last 2 zeros we're not sure about. So I'm going to tell you those were measured. It was 500 measured to the nearest mill. So I filled in my I's. I put in 2 zeros for the products. There was no mention of the products at the beginning. And we have a question unlike any other. We know all the I's, but we don't know any of the changes. We don't know any of the E values. Okay? So this is the I and a KC type question. This is what that middle option looks like. And you have to identify that this is the type of question that you have to use a variable and solve for the variable. Okay? The variable is going to go in for the change. Okay? Every unit of change is going to be an X. Okay? Now this first question I'm going to do is going to be fairly straightforward. The coefficient here is one of those. So our change is going to be 1X. And it's a reactant, so we're going to lose an X. Our second reactant, okay, all our change is going to be based on X, and there's 1 water. So that's also going to have the same change as our other reactant, 1 unit. You've probably picked up the pattern now. Whatever the coefficient is, that tells us how many units of change we have. A 1 there, so that's a change of x, but that's being made, so it's going to be plus, and there's one of those, so we're going to get 1 unit of this change. Okay. Now the 1s only confuse things. I wanted to emphasize that the stoichiometric coefficient turns into our coefficient in front, but we don't write 1s. I'm going to get rid of, no, I'm just going to go minus x. It's clear in mathematics that we never write a 1 coefficient in front of an x. Okay. So now I can fill out my whole ICE table, plug it in an equilibrium law expression. I have 1 variable. I can solve for 1 variable. You can solve for 1 variable. So 4.00 minus x, 4.00 minus x, 0 plus x, so that is just x, 0 plus x, so that is just x. So we've solved for our e's, but they're algebraic. And I'm going to plug everything into the equilibrium law expression. And this is why you took math class. You're going to use some of those skills your math teachers taught you. Everybody loves algebra, I hope. Luckily, you'll find in Chem 30, the questions are rigged to make the math simple. So you'll see all of these questions be like, why do they put 4 moles per liter of both in? That's kind of like odd. Okay? It makes the math easy. If one was 4 and one was 5, this question would be 10 times harder mathematically speaking. So you'll notice that the rigging of the questions for the math. So Kc is 4.2 equals concentration of carbon dioxide. That is X. It's meant to be a little check mark. Concentration of hydrogen is also X. Well, I'll simplify that. That's just X squared. Divide by 4 minus X, and then we see it repeated again. So I'm going to drop the 0.00 just to make it a lot simpler to write. So I'm being a little ignorant of sig figs, but it makes this. Okay. And because it happens twice, I can square it. Now I'm going to keep solving. Okay. Again, all your questions are going to be rigged a bit. They're 4 minus x twice. If this was 4 minus x and the other one was 5 minus x, you'd have to FOIL it, collect all your terms, you'd get a quadratic, and you'd have to solve it. Okay? But there's something simpler here. What can you do here without foiling that and collecting all your terms because of the layout? Yeah, you can square root both sides. We have a square on the top and a square on the bottom. So we don't have to expand this. I'm just going to pull that square out. .2 equals I'm going to pull this square. I'm going to pull a square out of the top and bottom. Okay. The whole top is squared. The whole bottom is squared. So I've just pulled that square out. If it wasn't for the fact that there was a square on the top and a square on the bottom, the math would be much longer. Now, this can nicely be solved by square rooting both sides, and that gets rid of the square on the right side. So now I'm going to kind of just fly through the math. I'm going to do this quickly. 2.05 is the square root of 4.2 equals the red square root just cancels out the blue square. I'm going to cross multiply, collect my x's, and then I'll have the value of x. So I'll do the top to bottom first. I get 8.20 when I take 2.05 times the 4, and then I multiply it by the second term. So that is that cross. the green cross equals just x. And then I'm almost done. I want to collect the x's on one side. I'm collecting them on the right because that'll make positive x's. So that's why I'm doing it on the right. So 8.20 stays put. I move a bit over 2 x's to this side, so it becomes plus a little over 2 x's. But I already had an x. This is where you have to remember that that's 1x. So there's 2-ish. There's another one. There's a third one. So we have a little over 3 x's. Divide each side by the term in front of x. I cross the top and bottom out, which is equal to just 1 or 1x. And that's 2.68. Okay. Now, I left all my units out. I really do find students, if you write all your units in, it really clutters the math and can lead to an error because of unit analysis. So it pains me to say leave the units out. I'm normally the one who says always leave them in. But this is a unit, you may leave them out. Just make sure you started with the right units. Okay, if you start with Kc in mole per liter, that x is in moles per liter, if you've been doing everything carefully. So almost done this question. Okay. So x is 2.86. So we know this is 2.68 moles per liter. This is 2.68 moles per liter. This E value is going to be 4 minus 2.68. That's 1.31. When I keep all the digits in my calculator and do the subtraction and then round again, I get 1.31, and the same here. So this is the first question. You'll see more. Okay. Another day, I'll do an example where there's some squares in it. In chapter 16 in the acid base, we'll use this technique again. Key is you have all the I's, you have a Kc, you have to use an X, write an expression. Do not go down some complicated math rabbit hole. Chem 30 is rigged to make the math straightforward. There's an assumption we're going to talk about that will simplify the harder questions. At no point should you ever use the quadratic formula to solve a question within Chem 30. In AP, we will solve some questions that require the quadratic formula, which is it's a very doable skill for you. Okay. One last sort of slide on this original theme, and then I've got a last harder example like this, and then you're going to have some work time to digest all of this, because I know you've gotten a lot. Now, I think what happens to Kc if we flip an equilibrium equation. Okay? We know they can go both ways, so what if we just wrote it the other way? What would happen? We're going to do a little bit of a case study or an example. We're going to flip it and see what happens. We'll make up some numbers and see what happens to the numbers when we flip it. So I'm going to start with a generic equation. Some A chemical plus B chemical is in equilibrium with C, and Kc1, this is going to be my first equation, so I added a 1 after my Kc, has a value of 4 units. Okay? So it's product favored. Or specifically, it favors C. I'll just say C and leave out the brackets. Okay. We're going to flip stuff, but we want to keep that emphasis. This is product favored. It's going to make more than half of the amount of C it could make. That makes it product favored, and we're going to see no matter what we do to it, it's always going to favor C. Our equilibrium law expression would be C divided by A times B. We've done that. Okay. Now we're going to get into what we want to. We're going to flip things. So I wrote C at the beginning and A and B at the end. So I wrote it the other way. Okay. This is going to be equation number 2. And I put in Kc2 so I can separate Kc1 from Kc2. And what would Kc2 be? Well, let's look at the equilibrium law expression, which is products, A times B to the first power divided by our reactants, which is C. And then my question for you, and I know once you're done writing, is how does Kc2 and that expression mathematically relate to the first one? First is a nice short way to say that, 1 over Kc1. Okay. So when you flip an equation, products or reactants, you have to inverse the Kc value. So 1 over Kc1, which, well, we know Kc1, that's 4. So this would be a quarter, okay? Which, that's less than 1. So this is reactant favored. It's going to favor the beginning, which is C again. So we haven't really changed the chemistry. We flipped it around. It still favors C. It's going to use up most of the A and the B. It's going to make mostly C. No matter which way we write it, we still get that fundamental science.